Franco, you said you wanted to host, or were you meaning the Zoom session?
Yeah. Someone has to introduce the speaker. Yeah, Fabi, go ahead.
Okay. So Jacob Phil Grevstad from the Norwegian University for Science and Technology. Thank you for accepting our invitation to speak here. We're happy to have you here. You can start whenever you want.
Yeah. So yeah, thank you for having me here. Thank you for the introduction. So I want to talk about some recent work I had with Erlend Børve and Endre Rundsveen about concealed algebras and g-tame representation type, as it says here. So before I say more about what this means, I would like to have this little diagram that illustrates what the main theorem is. So in, representation theory of algebras, most of us maybe are familiar with that we can divide our algebras into three types. You have those of wild representation type, tame representation type, and finite representation type. And then in the setting of tau tilting theory, there is, there is some similar divide, or maybe we would like to extend this notion is what I should say. So there is the concept of tau tilting finite, which then includes all the representation finite, but it's not necessarily equivalent. Like you can have both wild and tame algebras that are also tau tilting finite. And there's this concept of g-tame. And there may be also some other competing notions. But we have this concept of g-tame that generalizes the idea of being tame, and it extends. Also, there are some wild algebras that are g-tame, so it's not like a perfectly corresponds to tame. And then what we have been able to show is that concealed algebras, they live right here at the top. So they are wild precisely when they are not g-tame, and they're finite exactly when they are tau tilting finite. So they, for algebras in general, right, we have this more complicated cut right here, but the concealed algebras are right here. Right. Okay, and then I wanna spend I guess most of this talk defining, okay, so what is g-tame, what is a concealed algebra, and like what sort of tools go into this proof. So yeah, and I have some quick notations, right? So we look at finite dimensional algebras over an algebraically closed field, okay? When I say modules, I always mean finite dimensional left modules. As I say something in reference. Use this notation absolute value of M to mean the number of non-isomorphic and composable summands of M. And and usually I don't assume. So sometimes I say something where I actually need the module to be basic. So it doesn't have any repeated summands. It's not super important, but maybe I say something where that's necessary. Okay, so then let's just jump into some definition maybe most of you are familiar with is the definition of a tilting module. So here we have, for simplicity, we work over a hereditary algebra, or not for simplicity, but there are many definitions of tilting and generalized version, but classically, they're over hereditary algebras. And that was a module which was rigid, didn't have any self-extensions. And you could find this exact sequence where A was sort of resolved by some direct summands or something in the additive closure of your tilting module. Yeah, and another then characterization, which is useful, is that tilting module is like a rigid module that has enough summands. So in this hereditary context, this is very nice, and then these are generalized in many ways, but before I get to that. So one sort of key thing that we use about tilting modules in this work is the Brenner-Butler theorem. It's here that, okay, so we have the same setup. We have a tilting module, and then this endomorphism ring of the tilting module is called a tilted algebra. And T becomes a bimodule over so the original algebra and this tilted algebra. And we get equivalences between this subcategory of quotient modules or factor modules into some subcategory of mod B. And yeah, similarly for this. So, and yeah. And the sort of important part here is that these two subcategories that we have here on the right, they sort of they become what is called a split torsion pair. So they sort of split the module category of B completely. So we can understand all the B modules by studying these two categories. So I thought, so maybe most people here are already familiar with tilting modules, but I thought I would do a very quick example that we could have in mind. So say A is this A3 quiver, or the path algebra of this, and its AR quiver would look like this. And we can find a tilting module consisting of these three summands, right? So P3 plus P1 plus S1 here is the tilting module, and the endomorphism ring B will look like the same A3 quiver, but with the relation. And then what is this Brenner-Butler theorem? So we have this the factor modules over tilting module, right? So this one, this P3 here doesn't surject onto anything, but P1 surjects onto I2, and yeah, in total, these become the indecomposable modules in this fact-T category. And the other one was the submodules of tau. So if we apply tau to these guys, these just go to 0, S1 goes to S2. So submodules of this would just this one guy. Okay, and then, yeah, over here, the AR quiver looks somewhat similar. And then you have here this red part and this green part. Okay, right, so through these Brenner-Butler functors, this is mapped like this, right? So this red part is moved into this chunk, and this green part is moved into this chunk, and we can see the whole AR quiver of B. Okay. Yeah, so that's just highlighting. So the important of this is that we can understand all the modules of B by looking at these sort of subcategories in A. So B is very close to being hereditary. Let's see. Okay, and then, yeah, I said there are many generalizations of tilting modules, and because tilting modules have, come up in many contexts, and therefore are many important properties one would want to generalize. And one thing is that they have a very nice combinatorial structure. And when you want to generalize that combinatorial structure, then the correct notion is support tau tilting. So let me also then define this. So we say that a pair of a module and a projective module together is a tau rigid pair so first of all, there should be no homomorphisms from M to its AR translate. And there should be no homomorphisms from the projective to M. And then it's called support tau tilting if the number of summands, so meaning just the sum of the number of summands of M and P, is the same as the number of summands of our algebra. So these conditions here sort of encapsulate this X1 condition of our tilting module, or maybe really the first one sort of captures this X1 condition. And then we have this condition on the summand. So this is, in that sense, a generalization of this definition of tilting module, or at least this property that tilting modules have. And then some very nice thing about support tau tilting modules, or the property that they sort of generalize, is that if you have a tau rigid pair that's missing just one summand from becoming support tau tilting, and then there are exactly two ways to complete it. So so if you take a support tau tilting and remove one summand, then there's exactly one other summand you could replace it with, and thereby you go from one support tau tilting module to another by replacing a summand, and that's what you call mutation. Yes, and this existence of mutation gives a very nice relationship on the set of support tau tilting modules. And so also for those who are familiar with tilting complexes, sure. And I also would like to mention quickly that if you have a tau rigid pair and you take a minimal projective presentation of M, and then you sort of add in the P part at the second term, or this degree 1 term, then you get a pre-tilting complex, and that this gives a bijection between support tau tilting pairs and two-term tilting complexes. So you can study this then. If you want to study this through the derived category, then you would look at these two-term tilting complexes. Okay, so that's in some sense a digression, but it's also important for this definition of G vectors, which is then important to define what g-tameness is. So when we have such a tau rigid pair, then we can define the G vector to be this. So we look at this pre-tilting complex that we described before, and we look at it in the Grothendieck group of the projective lambda modules. So in this Grothendieck group, I won't say exactly how to define it right now, but what it is basically is that it's a free abelian group generated by the indecomposable projectives, and then the representative of this class, this G vector, will just be this first projective minus these projectives in the other case. So you can think of it just a vector that says, which projectives appear in this resolution. Yes. Okay, and what can we do with this G vectors? We can make a G vector fan. So that's where we're going. So if we take a tau rigid pair and decompose it into indecomposables, so meaning that indecomposables are either just one summand of M or just one summand of P. And then we can define this the cone of this tau rigid pair to be all just non-negative, so AI here, non-negative real numbers, non-negative linear combinations of the G vectors of all this. So this is called a cone because if you sort of think of it in Rn, it forms a cone shape. Yeah. And then we also have this sort of interior cone where we use strictly positive instead of non-negative. Okay. Right. And this cones, all these cones together form a nice combinatorial structure or combinatorial geometric structure. So if we take the union of all these, then we get a polyhedral complex. So these interior cones, they don't intersect each other. At least if NP is basic tau rigid pair and they're different. So then they sort of divvy up the space in some way. And we can also think of it here, these will overlap and they will give you a simplicial complex. But yeah. Okay. So maybe we do a quick example of this also for A2. We have A2 here and we like to draw the AI quiver here. So then we see what all the modules are. And then what are the tau rigid pairs? So at least the indexable ones are then P20, P10, S10, and then the projectives in the other coordinate. And what are the g vectors of these? So if we just label the g vectors by their projectives, so this one has just the first projective, so that'll be just the first projective and then nothing of the other one. And this guy is just the second projective. It's going to get a vector like this. And S1 is more interesting because its projective presentation looks like this. So we have one of the first projective and then subtract the other projective. So 1 minus 1. Yeah, and then these 0 and these guys are just the negatives of their projectives. So 0, -1 and 0, -1. Sorry. -1, 0 and 0, -1. Yeah. And if we draw this in the plane, so we have them. This one was there. This one was there. This one was there. This one was there. So this was P2, P1, S1, and then we had this P2 and P1 in the, I write this shift just to mean that they are in the other coordinate in this pair. And then we take the cones that these guys span, all possible positive linear combination of them. We get this. And then sort of the magical thing here now is that the sum of, for example, P1 and S1 together form a tau rigid pair, and they are also next to each other in this diagram. So in here, we get the cone of P1 plus S1. And then similarly in here, we get the cones of these edges. And in this case, it filled up the whole plane. And yeah, but in general, you might not fill up the plane. So let me now, without going into this much detail, look at something like the Kronecker quiver, which has, so by this I mean there's 2 arrows. Then it looks somewhat similar. we still have these edges right here. Then we have some things right here. Then we get more and more of these one-dimensional cones, and they pile up. And then there's a little missing line in here where there are no cones. And similarly, if we had 3 arrows, and we get also a very similar picture where we have these, then we have some one-dimensional cones here, and they also get denser and denser, and then they sort of pile up 2 different spots, and then we have this big empty area with no cones. Okay, so what can we learn from these 3 examples? Well, we say that an algebra is g-tame if its g-vector fan is dense. So looking at this example, here we have the g-vector fan covers the entire plane. Well, it's dense. Here, this guy, it doesn't cover the entire plane. There's this part missing, but this is a very tiny piece. If we take the closure, then we get everything. Okay, but this guy right here, there's like a big piece missing. Okay, so when we take the closure, there's still, okay, we get a little bit more, but there's still a lot missing. So this guy is not g-tame, but these guys are. Yeah, and then maybe we'll also notice here that, so A2 and the Kronecker, they are actually tame, while this triple Kronecker is wild. So we have this distinction here that this, at least in this case, being tame coincided with being g-tame. And yeah, and that's a little note I have here. So this is somewhat by Plamondon and Yurikusa. It's just that tame algebras are always g-tame. So just like we saw here we have a tame algebra and we got a dense g-vector fan. Yeah, but in general, the converse is not true, like sort of said at the onset here, that we can find wild algebras that are g-tame, but all the tame algebras are at least g-tame. So it works as a generalization in that sense. Okay, and then how? So how can we, or what tools did we need to understand these g-vector fans in our results that I'm talking about today? And one key result is this wall and chamber structure, which is in some sense just a different way of realizing the g-vector fan. I mean, at least it's very, very closely related, at least. So if we look at, so we look at the Grothendieck group of the projectives and the Grothendieck group of arbitrary modules. And has a pairing, which is just taking the dimension of this home space, at least for when we're just looking at a projective module and a module. And we can think of this, so if we think about, like we did before, as an element of this Grothendieck group, as just a vector that's specifying where the projectives are, and we think about an element of this Grothendieck group as a dimension vector of a module, then this pairing is just a normal inner product. And then if we want to work with real coefficients instead of just abelian groups, then this pairing, of course, extends linearly by just multiplying by real numbers whenever necessary. And then we usually use this notation for the pairing. So here, theta is something in the real Grothendieck group of projectives, and M is a module, or maybe even something in the Grothendieck group. Okay, so this is just a lot of notation. But then we can define a wall. So wall is again something that lives in this space of this real Grothendieck group. So in the previous example, it was in a plane. And we look at all these vectors of projectives such that for a given module, okay, so we have a fixed module M, and then we want to define the wall that belongs to M. So this vector, this theta, needs to be orthogonal to M. But further, for any factor module, for any module in fac M, it needs to be non-negative. Okay? So it's almost the orthogonal complement to M somehow, but a little bit restricted to be like in one direction. Maybe that's a way to think about it. And yeah, so what then theorem due to psi, I believe, is that if, so formulated a bit differently maybe, but we can look at the G vector fan. Now we look at only the maximal cones. So forget about, so maybe if I go back, right here, we only think about these here, these maximal cones, these which are two-dimensional in this case, the cones of maximal dimension, and forget about the one-dimensional ones, and even 0. Then together with the walls, these fill up, so not necessarily the entire real Grothendieck group, but at least the entire Grothendieck group. And also, if you take the closure, then you get the entire real Grothendieck group, right? So there's some irrational numbers and things like that may be missing from here. But at least if we take the closure, we get everything. And also that these are disjoint. So all the walls live away from these maximal cones. So we can sort of split the space up into where there are maximal cones and where there are walls. And yeah, so in particular, there's means that we can understand if an algebra is g-tame by looking at the walls. If the walls are dense in an area, then there can't be any maximal cones there. And because cones always sits inside these maximal cones, or at least inside their closure, if there's a dense set of walls, then there can't be any cones there, actually. So then we're in this third case where the G-vector fan is not dense. Okay, so if we can understand, when are the walls somewhere dense and when are they nowhere dense, then we can do that. And then, yeah, so I think we can quickly, so let's try to verify this here in this quick example. So again, we look at A2 and the AR quiver is right here. Now we think of these, so we have these 3 modules and we look at the real Grothendieck group here again. And then, so okay, one module here. If we think of their dimension vectors now instead of their G vectors, then we have this guy is simple, supported only in the second degree. This guy is simple, supported only in the first degree. And this guy has one composition factor of S1 and one from P2. So it looks like 1, 1. And now the G vector that is orthogonal to this guy, I mean, that would just be something that doesn't have any y component, right? So this entire line would then be the wall at P2, or belonging to P2. And similarly, things orthogonal to this guy is things without x coordinate. So right here we get the wall belonging to S1. And now things orthogonal to this guy, I mean, that would be something like living on this. But now we have to also remember this condition that it should be positive for factor modules. Okay, what are the factor modules of this guy? Well, that's S1. So it has to have a positive or at least non-negative x coordinate. So excluding this part. So the wall looks like this. Oh, P1. And as you can see, it looks exactly like the G-vector fan, or at least the part that without these maximal cones. Okay. So, yeah, so what was the idea here? So we want to understand these concealed algebras, which I haven't defined yet, but they are closely related to hereditary algebras. So if we can first really understand how this works for hereditary algebras, then we can sort of extend those ideas. So what are the tools we have available for hereditary algebras? Well, hereditary algebras are very nice. So they have, for one thing, they have finite global dimension. So when we are in a case where lambda has finite global dimension, then we get this isomorphism between the Grothendieck group of the module category and of the projectives by just sending a module to its projective resolution. And yeah, and even further, when we're in the hereditary case, then the projective resolution is the same as a projective presentation. And remember that the projective presentation in here corresponded to G vector, at least if there's no projective in the second coordinate of our pair. So if we're just thinking about the module part, then the projective presentation corresponds to a G vector. Okay, so then we can sort of go between these 2 points, because when we talked about the walls, we sort of had this pairing between the projectives and the modules. And if we can go between them, right, then that makes everything easier. Yeah. And yeah, so that's what I said right here. We think of a module as its dimension vector. And now, in the cases where we want to think about G vectors, we can instead think about the dimension vector, because we can go back and forth between these, no problem. Okay. And now that we have this set up to how to understand it in hereditary algebras, then we can sort of lean on all these heavy tools and things that have been combinatorial tools that have been studied to understand hereditary algebras. So for instance, we have this bilinear form called the Tits form, or the Euler form, or the Euler-Tits form, which is, I mean, usually defined in terms of some combinatorics with the quiver, but an equivalent way to describe it is that given, a representative of a module, or a module in the Grothendieck group, then we can take the G vector of this module and the dimension vector and take their inner product. So this is this pairing mentioned earlier. And an alternative way so if you expand out this and do some computation, you can see that this is the same as the dimension of the Homs from M to M minus the dimension of the X space here. And yeah, and this only depends on the dimension vector of M, right? So this definition sort of makes sense, right? Here I'm just talking about dimension vector, here we're using the actual module. And again, we extend it bilinearly to real coefficients. So we have this nice bilinear form, and then there's a theorem, classic theorem, that A is wild representation type if and only if this bilinear form is indefinite, which you can make slightly stronger by saying that it's not only is there like some vector where it's negative, but this actually is the dimension vector of an incomposable module. Okay. So now we have, so this quadratic form, which then relates to this vector here, which seems, this definition here seems closely related to the definition of a wall. And now we know that this becomes negative, which is also related to this definition of a wall where we want the thing to be positive, right? So these are some tools that seem helpful, at least to understanding the hereditary case. And we have even more tools in what's called hyperbolic hereditary algebras. So hereditary algebra, or maybe actually an arbitrary algebra, but in this case, I will only consider it for hereditary algebras, is called hyperbolic if it is wild. But for any non-zero idempotent, if you mod out that idempotent, then it becomes not wild. So it's like a minimally wild. It's wild while being as small as it can be, basically. And then, yeah, so for hyperbolic algebras, this bilinear form, the states form, is even nicer. Namely, if we have some integer vector such that the bilinear form takes the value of 1 or less, so 1, 0, or any negative number, then there is an incomposable module with x as its dimension vector, or possibly negative x, right? Because exchanging x for negative x doesn't change the bilinear form. But if, say, x was positive, then it would have to be a dimension vector, because we never can't have a negative dimension vector. Yes, so this makes hyperbolic algebras. If we want to understand, what the modules are and what this bilinear form, we really just have to look at integer vectors. Right? We don't really have to think about what the modules are at all, which is, which makes things very nice. And so in particular, we can think about this set of real vectors where this bilinear form becomes negative. And then, yeah, so from what we said before, if A is wild, that happens if and only if there is some positive vector inside this cone. And then by, so continuity with the real numbers, this should happen if and only if it's non-empty. So at least for a hyperbolic case, but also in general, you can see this. Yeah, so we have this cone that sort of measures whether A is wild or not by whether or not this cone is empty. Yes, it's the point.
And this cone has measure greater than 0, right?
Yes, it's an open.
It's a proper open cone in Rn.
Yeah.
Right.
Yeah, so it could be empty, but if it's not empty, like when A is wild, then it will have some positive measure. Yeah, exactly. And yeah, so this cone sort of, so the way we formulated it sort of naturally lives inside this real Grothendieck group of the modular category. But like we said before, since A is hereditary, we can think of that as the projective Grothendieck group, and so when I reason about it in the future, from now on, I will think about it as though it was in here, even though maybe this definition is then confusing because positive in the modular category and positive in this Grothendieck group maybe means different things, but we define it in here and then just think about it like it wasn't there. So then if we think about it being in here, then we can intersect it with the walls. And then, yeah. So one thing, so I haven't written anywhere, but this cone, this which I call the negative cone, does not contain any of the cones in the g-vector fan. So that means then, so because the walls should cover the complement, or like should be dense in the complement of the g-vector fan, and this guy is an open set, if we intersect it with the walls, then we get something dense in here. So if we can sort of control the balls that are inside this cone, then yeah, then we can understand when it's empty and when it's not empty. I mean, if there are no walls in there, then it's empty, and if there are walls in there, then it's not empty. So that's, yeah, it doesn't sound like an interesting statement, but it will be useful. And what is it we want to use this information to? It's to understand concealed algebras. And I want to say that concealed algebras are like almost hereditary algebras. And so what do I mean by that? Well, we say that, so we have a quiver Q, and then we say that lambda is concealed of type Q if it's the endomorphism ring of a tilting module. So remembering the very beginning, we talked about tilting modules, then we have this tilted algebra. But now, very importantly, T is supposed to be a post-projective tilting module. So what does that mean? That means, so if you think about like the AR quiver of KQ, it usually has like this shape where the projectives are here, the injectives are here, and then you have the modules that are AR translates or inverse AR translates of the projectives, they live here. And the ones that are AR translates of the injectives, they live here, and then you have the regular modules in the middle. Now, being post-projective just means that all the summands live here in this component. Okay. And why does this make it almost hereditary? Well, because when T is post-projective, then this factor category, factor module of T, they contain almost all the modules. So except for finitely many, it contains all the modules of KQ. And similarly, this corresponding category on the lambda side also contain all but finitely many. So then this Brenner-Butler functor, this equivalence between this category, is then almost an equivalence between the module categories because it's only missing finitely many modules, right? So mod lambda is really close to being the module category of hereditary algebra. Right. And then the hope is that since we now understand the g-vector fan and the tau tilting structure of mod KQ very well, then this would translate to understanding mod lambda. Okay, so yeah, so then one result we have, so we are in exactly this setting where lambda is I didn't write, yeah, concealed of type Q. Lambda is concealed algebra. And now Q is hyperbolic, so hyperbolic hereditary algebra. Then, so this first part may not specific to being hyperbolic, but we have an isomorphism between these Grotny groups, which sends, so for the Ti here are the summands of T, then we send the G vector just to this projective module. So this home T here maps the summands of T to the projective lambda modules. And now we do the same with G vectors. And because you can show that because T is a tilting module, the G vectors here span and actually form a basis for this Grotny group. So this actually extends to a map on the entire thing, and it becomes an isomorphism. Okay, and then some of this important part if we have something in this negative cone and that vector is contained in a wall, then when we apply this isomorphism here, the image vector will also lie in the wall. So here we're using everything that we've said thus far. So really about that, because KQ is hyperbolic, we can study the vectors instead of looking at the modules directly. And then we can use these properties. So it's basically just writing out all these properties and doing some computation shows that this must again be in this wall. Okay, but then what does this mean, right? So inside this negative cone, so if K is hyperbolic, it is wild, it has a non-empty cone, which has some positive measure, and inside there should be lots of walls. The walls should be dense inside there. And now we're saying that when we apply an isomorphism, moving it over to the real Grotny group of lambda, then all the vectors that were inside walls are again inside walls. Okay, so then we have a dense region of walls inside the Grotny group of lambda as well. And that means lambda is not g-tame. So exactly what's written here, if KQ is not g-tame, then lambda can't be either, because we have this dense region area of walls that is simply moved without being changed. Basically, it's the same walls, just kind of moved. Okay, and this was for, right, so in this here, we're sort of using that Q is hyperbolic, but luckily we have some sort of reduction techniques. That's, if we start with an arbitrary wild quiver, then we can use some reduction or maybe an arbitrary concealed algebra of wild type. Then we can use some reduction techniques to get it down to one that's coming from a hyperbolic quiver. And then because this notion of g-tameness works nice with these reduction techniques, then we get it for all concealed algebras. Yeah, so really we did it for a hyperbolic case, and then the other part, to reducing from general case to the hyperbolic case, is somewhat straightforward. At least you will use some results about the theories of things set up by Plamondon and Yurikusa, for instance. Yeah, and this is sort of, I sort of think of as the main theorem, but our original motivation was not to understand concealed algebras. I mean, they are very close to hereditary algebras, so maybe it's not so surprising or exciting that they behave similar to hereditary algebras. But the reason we started looking at them is really because we wanted to understand incidence algebras. So meaning the algebras that describe the representation theory of a finite poset, partially ordered set. And so we knew about this theorem of Leszczynski, which says that an incidence algebra of a finite poset is wild if and only if its universal Galois cover contains a hyperbolically concealed algebra as a convex subalgebra. Okay, so this is this is sort of a weird statement maybe, but these concealed algebras appear here. So we can understand when a poset is wild by understanding concealed algebras. And there is this problem maybe of we don't really maybe understand what the universal Galois cover is, or if we understand what it is, but we don't understand how it interacts with this setup. But at least for simply connected posets, which cover quite a wide range of them, then the universal Galois cover and the posets are just the same thing. That's what it means to be simply connected. And so then we see that it's wild if and only if it contains a hyperbolically concealed algebra within it. And then with the same type of reduction techniques as before, then it would be g-tame if it only is tame, because the representation type, or the tau tilting representation type, would be controlled by this concealed algebra it contains. Okay. That's all I had to say. Thank you for your attention.
Thank you very much. Are there any questions? I have a question. Thank you, Jacobo. The talk was very nice, and I really liked your results. Do you think that you can get numerical criteria for all tilted algebras using this CAC result?
I'm not quite sure. So we sort of, so it's a thing we sort of use or lean on when we do this thing with the negative cone about about the walls there being transferred. Then we use that the regular modules of the hereditary algebra and the regular module of the concealed algebra are the same.
Right.
For general tilted algebra, right? Then the tilting module will maybe lie inside or past the regular modules.
Yeah.
Have that kind of control. But if you could,
if you could,
maybe you could argue something about that most, like in cases where most of the regular modules were the same or something like
for
that.
hereditary algebra, yeah, exactly. So that was I was thinking, right? I mean, for hereditary algebras, you can sort of understand which are your quotients just simply looking at the dimension vectors, right? Because this from the and therefore trying to see what would be the intersection of this negative cone that you have with the factor models, and maybe if this is, I mean, using the same result, right? When this gives you something of measure different from zero, and this will give you some negative cone in the tilted algebra, right? Using the Brenner-Butler theorem once again.
Yeah, so I haven't thought about the details too closely, but it's possible that you could maybe do something like that. But it has to be like maybe a strong criteria, right? Because
maybe.
algebras in general could be pretty different from, like, if you start with a wild hereditary algebra, you can still have finite representation type of your tilted algebras and so on.
Of course.
And it can be very dramatic.
Right.
So I don't know what would be the right criteria to look at necessarily.
So I was just wondering how, I mean, taking the dimension vectors of your tilting module, if you can sort of understand the factor modules as like a subcone of the Grothendieck group, and then you intersect this with your negative cone that you have calculated or that exists for this Q for at least the hyperbolic case, using Kak's theorem. And this intersection might be of dimension, I mean, of measure zero or not. If it is measure zero, then you would go from something wild, which would not be g-tame, to something g-tame. Because maybe not g-tame, but if the intersection it has positive measure, then using the Brenner-Butler theorem, the same results that you use here, you would get this sort of a negative cone.
It's possible you could do something like that. Yeah, I'm not sure. Yeah.
Cheers.
Yeah, thanks for the question.
Are there any more questions?
Yeah, I had a quick question, Jakob. Thank you for the nice talk. This C minus less than zero cone that you talked about, where this bilinear form is less than zero. Can you describe exactly the intersection of this with the walls? Like, if you have a dense region of walls, does this C less than zero cone somehow intersect with the whole region, or is it generally just a potentially small part of it? Like in the three Chronica, for example, what does that look like?
In the three Chronica, they're the same. So we actually tried for quite a while, actually. So we sort of worked with just this, so the complement of the G vector fan, or like the dense region of the walls, and sort of tried to prove that this is the same as the cone. Like, that was sort of our original approach, and we weren't able to do that. And I'm not sure, like, just from trying, it sort of felt like maybe it wasn't the case. Like, this negative cone should be smaller, But
Yeah.
I would be very curious to know, and this is, but yeah, in the sort of the two-dimensional case, they're always the same. But,
Okay.
but the two-dimensional case is kind of simple, right?
Right. And after that, it's a bit difficult to understand whether this will be.
Yeah, it's hard to compute.
Yeah, fair enough. Yeah, because that's okay. I thought maybe it is exactly basically the complement.
Someone could figure out whether those are the same or not. Something I would like to know, but I'm not quite sure how to approach it.
Oh, but it's still a very nice result you have.
Thank you.
Thanks, yeah.
Any further questions? Well, let's thank Jacob once again